אנחנו מקליטים.
כן. בזמן שהאחרונים נכנסים, אני אנסה כאילו אולי כזה להבין מי הקהל שעומד לפניי, זה תמיד טוב לדעת לפני מי אתה מדבר. אם הם גדולים לך בתורה, זה תפלצת. מי פה מגיע מהאזורים התיאורטיים יותר? אקדמיה, מפתחים, פרודקט, משקיעים. מאיפה, כאילו סתם נכנסתם למיטות ומצאתם... מה נשאר? מה אתה נגיד עושה?
פוליטיקה.
איפה?
היה מוצרת.
בתור מפתח אלגוריתם.
אני?
כן, למשל.
מובטל.
מדהים. בהייטק.
מובטל בהייטק.
זה נראה לי אחד החלומות, כאילו, נכון?
אבל גם אלגוריתמים.
אפשר לשאול אותך?
עושה בעיקר NLP.
מגניב. יש כאילו, אפשר להיות בספקטרום של ההרצאה הזאת יותר באזורים התיאורטיים, יותר...
Excuse me, is there a chance to switch to English?
There is a chance to switch to English. I would have to apologize because my English is not outstanding, but I think like if you want to be a startup nation, we should be able to speak English for the sake of this nation. So, there are lots of ways to do this talk. This one would be talking about how to boost your GAN training with TensorFlow and Tensor Cores. Tensor Cores, if you haven't heard of, we're going to talk about today, is an NVIDIA technology that boosts your training. It does not only apply to GAN training, we can do also NLP with it, we can do LSTMs or ConvNets, but for the most part, you'd find a lot of use case for Tensor Cores with GANs. And I'm specifically going to talk about how to do this on TensorFlow and on Google Cloud. But this is actually something that you would be able to do on your personal GPU, whether it's installed on your personal computer or your cluster or in any other cloud platform. So, generative models. What are generative models? The basic idea of generative model is to take some noise, or let's call it a latent variable or latent vector. And from this noise to create articles, they're actually samples that you would usually train up on a classifier. For example, for the sake of this זה נורא קשה להחליף אנגלית, אבל אני ממש אשתדל. אם נראה שזה הולך, אז אני אחזור לעברית. So basically, for the sake of this conversation, I would mostly be talking about images. So the idea of generative models is to take some random noise and then to put it into kind of a machine and generate something of a specific probability distribution. It can be, for example, images of geese. And there are several models, several types of family models. One would be autoregressors. You could also think about variational autoencoders. And this conversation is going to be focusing on generative adversarial networks. And generative adversarial networks started were first introduced, I think, in 2014, but the first applications were only visible in 2015. And these were kind of the vanilla results of generative adversarial networks. We're talking about this as an attempt to create an image of a flower, and this should be, I think, a flying bird. This is like a bird in a nest or something. The first initial results were not that outstanding, but the whole concept of a computer that can imagine or can generate data and not just tell us if it's a bird or a duck was kind of groundbreaking. And with time, we have seen a lot of progress, and there are lots of ways to make improvements upon the vanilla GAN. I'll be discussing about mostly a technology, a way to improve the training of GAN. But I will be also mentioning a few other techniques. So what can we do with GANs today? So nowadays we're able to produce really, really high quality images, really high definition. This is an example, I think, from last year that created. All of these are computer drawn anime figures, very high resolution, very nice. You cannot distinguish that it was not created by a human being or an animator. It was all created by a computer. If you know the content-aware completion in Photoshop, that is not based on generative models. That is what based. Actually, the person who invented it. I used to know her. She's a professor at Technion. Forgot her name. But you could do these content-aware completion of data using GANs. This is an example where you just hide this block from the computer and it autofills it. If you can see closely here, it says hotel, and the computer obviously did not know to put an L here, but the overall content seems pretty reasonable. You can see it completed a tree, and I don't know what that's supposed to be, but like it's smashed dog or something. And even some companies, in February I've seen a presentation by LMVH. It's Dior and Louis Vuitton. And Louis Vuitton is actually creating new samples of new patterns and samples for their bags collections. You can find patterns that were never have been created by a human being. All of them are generated by a computer. And you can actually see applications of generative models in the textile industry. So a lot of, I think that most of the applications that I've seen were relevant to computer vision, although you can basically generate any kind of probability distribution if you know what you're doing. So I've been talking about GANs, but what are the GANs? So I'm going to present the vanilla way of GAN, and there are some complications to the vanilla form that we can mention later. But this is like the vanilla GAN that was presented in 2014. And the idea is basically to have two networks. One of them is a generator, and the other one is called a discriminator. And the generator has a very specific role. It has to take noise and output. I said we're mainly talking about images, so I'll just refer this as images. Let's say I have the MNIST data set, so I have this training set of images. So the generator would try to generate pictures or images that look like the images of the digits that are in the data set. Not necessarily exactly like the images that you would find. So it would look like very similar, so you wouldn't be able to distinguish between an 8 that was drawn by the computer or an 8 that appears in the data set, but it's not necessarily identical. Or you would rather it not to be necessarily identical. And the other network that we were talking about is the discriminator. Now the discriminator is basically a convnet, a very standard convnet that accepts fake image or training or a real image as an input and tries to output if it's a real or fake. This is very, very common use case of convnet to have like an input image and then try to assign it to class. And how do you train this kind of system? So this is why it's called generative adversarial networks. Basically, these two networks competed against each other. The first one, let's start with the second one. The discriminator, as I said, has to distinguish whether it was a fake image or a real image or a genuine image. And it's really, let's say I have a well-trained discriminator. I would train it on the MNIST, and I would put in a fake image, then it would probably be very, very easy to distinguish. So the generator has to learn how to trick the discriminator in order to confuse his labels. So basically the loss for the generator would be the negative, for the most part, would be the negative loss of the discriminator. So the discriminator is given a set of samples of fake and real images, and it has to distinguish between them, and it has a loss over this image, over this data set, passes the loss to the generator, and then the generator tries to learn new techniques to improve the image generation in order to create images that are more and more like this training set. Yes?
So you said that you would have a discriminator, but if you're training it on n-lists, it will just know how to separate the digits and it will be very good at telling you if it's from the data set or not from the data set, right?
Yeah. Yeah. Okay. So what I was mentioning, what I was referring to, what I was trying to say was that if I have a very good discriminator, then basically, and this is what one part of one problem in training generative models or GANs is that if the discriminator is very good at what it's doing, then it won't be able to. The generator would never be able to understand how it should change the parameters in order to generate better and better models. So the training of these two kind of has to go together. You cannot start with a very good discriminator. Both of them has to be initialized kind of to the same random values at the beginning, and then when you train them gradually together, the discriminator gets better and better, and then the generator can learn gradually how to generate images. Okay, if that was not clear. So let's look at how the training process would look like. So this is the images they're generated, I think, for an AC GAN, kind of GAN that also learn to classify the images. I'm giving it a classified data set. And what you can see here that over time, the images that are generated by the computer kind of get the shape of what you can tell as a 4 and a 1 and a 6 and a 0. So this is basically how it looks like during the training. And let's talk about what specific difficulties do we usually have when we're training generative models. Okay. So first of all, as opposed to regular classification or regression problem, we don't have a very good function that could tell us if we're doing right or wrong. Because there is no function that can tell us if this 9 looks like a real 9. We are actually kind of learning this function within the discriminator. So part of the solving the problem is actually learning how to solve the problem. And that's really not a good practice for science. But it brings very good results. So it's kind of a tricky way that in order to solve the problem, you have to learn how to solve it. It's like when they tell you, how do you search for love? You don't search. When you find it, you know it. This is why I'm single. Okay, so and so you don't have a very distinct, simple way of finding if you're doing a good job. Another thing that we mentioned before was that you have to train them together, because if the discriminator is really good, the math behind what I was saying that the generator would not know how to generate better images is that the gradients would basically all be 0. Because no matter what the generator is generating, it's always, the discriminator is always telling you, no, I can figure it out pretty easily, this is all fake. So it means that no matter what you're changing to get the same result, the gradients are 0. Another problem that you might have is that it's very complex target distribution. As opposed to when you're trying to estimate a probability distribution when you're training a classifier, the generator actually is trying to imitate a very complex probability distribution, and basically talking about images of people or images of cats or images of digits. It's a much higher dimensional complex probability distribution that we're trying to imitate with respect to, I don't know, cross entropy of probability distribution in a classifier. And another thing that we also encounter is the quality variation trade-off. If we were able to overfit on our training set, we would always generate images that are look exactly like the images that are in the training set. But we don't want that. We want a general model that can generate new images of digits or of human faces that is not exactly the same to the images that are in the data set. And let's just see. I'll see. I close the tab. It's called this person does not exist. Have you seen this? Must be. So these are all images when I kind of refresh it. I think that when I refresh, I get a new image, and all of these images, I think that are generated online, like per my request. So these are all people that do not exist. These are images that are generated by generative adversarial network in a technique that we're going to talk about in the next few slides. And you can see here some like errors that the model have. Question.
How do they know that these people don't exist, that they're not actually
Part of the data set, you can actually search. It was not built on a huge data set. You can actually search for this particular image. This person does not exist in the image. And they also, I'll be mentioning it in a few seconds. Okay, so a major advance in generative adversarial network training was made by NVIDIA last year. In an article that they call Progressive GAN Training, they were able to create images of celebrities that do not exist. For many people, if I ask you if you know these people, you would say that they look familiar, but these people are not actual celebrities. These are just generated images from a huge data set of celebrity images that was from a GAN that was trained on this kind of data set. And what NVIDIA did is that they understood that you don't have to, and another thing that I forgot to mention, that the images that I showed you before are really high resolution images. They're not just 64 by 64 images or 32 by 32 images of digits. These are really high definition images. So what NVIDIA figured out that the gradual process, the quasi-statute, of this process is extremely crucial towards the training. You cannot go and directly train the 1024 squared pixel images, but you have to go through first 4x4 images, pixel images, and then 8x8, and then gradually add more layers in order to be able to produce by the end of the training process very high definition images. So this is like the kind of scheme of the training. You have the generator here. It accepts a 4x4 latent matrix. It's what we call the noise. And then the discriminator accepts this 4x4 matrix and then tries to output a blurred image of this data set. And then with time, we just give them more and more complex images. So this is kind of the progress that was made, kind of summarizes the process that was made throughout the last years. So these are another classic example of generated images of hotel rooms. So in 2016, these rooms were kind of smudged or disoriented. And in 2017, you could see some kind of an improvement. But then our refers to NVIDIA's progressive GANs. Very high quality of also hotel rooms that are all generated with this technique. So when we're training GANs, or generally when we're training neural networks, we have a few ways to increase the training speed. And why am I mentioning it? Was that this GAN was trained for over 10 days in order to achieve these kind of results over multiple GPUs, very powerful GPUs. So it's extremely difficult to do research or you do R&D when you have to wait 10 days and only then you can discover if your results are real, if you're going in the right directions, especially when we're talking about GANs, that the loss is not really telling us anything. If I'm taking a look at this very schematic plot of the loss, then you can actually see that at the beginning the discriminator loss is extremely high, and the generated loss kind of increasing towards the end of the training. But these numbers don't really tell me anything. Looking at the loss when training GANs really don't mean a lot. They can kind of indicate which part of the system is stronger right now, if it's the discriminator or the generator, but I cannot know like what is the quality of images that I'm getting from this kind of loss. So it's not really comfortable to do research when you have to wait 10 days in order to get results. So let's say I was training just a regular network. What could I do to increase the speed of the training? So first of all, I could increase the batch size. But when training very high resolution images, I would find out that it's not really easy to put in a lot of GPU memory has a strict limitation, and it's not very easy to pack a lot of high resolution images to one batch. So it doesn't really work for high resolution training and GANs. I could think of ways to distribute my training over several GPUs, and it only complex the problem. Another thing would be to increase the learning rate. But as we mentioned, we don't want the discriminator nor the generator to make very large moves, like very large steps, because then if the discriminator makes like a substantially large step, the generator might get lost in the gradients. It can end up in the vanishing gradients. So that would not work for GAN training. Reduce the I/O overhead. For example, if I have overhead from reading from the disk or network or something like that, that could also work for GAN. Change the architecture. Optimize for the architecture. Lose unnecessary weights, lose unnecessary layers, reduce the size of the layers might also affect. And obviously, the main key point of our conversation would be how to improve the hardware. So we can use improved hardware in order to train GANs. For example, more RAM would result in being able to increase the batch size, or if our GPU can perform more teraflops per second, then we are able to train faster. So for this, NVIDIA came with a new technology that is called Tensor Cores. What are Tensor Cores? Basically, it's a way to, they're registers on the GPU that are able to perform 4x4 matrix multiplication and some addition. So it multiplies 4x4 matrices and then just add them, and that's all in a single clock. As opposed to the previous architecture,